Okay, today we're gonna go deep, like microscopically deep, inside a microchip. We're gonna uncover this absolutely critical process that makes sure your phone, your computer, all the tech you can't live without, actually works when you need it to. It's called dynamic IR analysis, and trust me, it's the secret sauce for making reliable chips. But let's start with a question, just to set the stage here. What is the silent killer of modern microchips? Now, it's not heat, it's not some physical crack. Nope. It's something way faster and way more sneaky. It's an electrical ghost that can bring a billion-dollar chip to its knees in less than a nanosecond. To get a handle on this killer, you've got to understand the two ways engineers look at a chip's power. First, you've got static analysis. Think of this as the average story. It's kind of like knowing the average traffic on a highway over a whole day. It's useful, sure, but it totally misses the chaos, right? But then you have dynamic analysis, and that is the real story. That's like looking at the exact same highway at 5 p.m. on a Friday. You see the gridlock, the sudden surge, the very thing that can cause the whole system to crash. And that brings us right to our first big point. In the world of high-performance chips, just relying on averages, yeah, that's a huge, critical mistake. See, the problem with static analysis is it makes some really dangerous assumptions. It pretends there's this nice, constant flow of electricity. It completely ignores the precise timing of when millions of tiny switches are flipping on and off. And because of that, it has this massive blind spot. It totally misses the gigantic, instantaneous spikes in current that happen in the real world. You know, the very events that cause a chip to fail. And when those spikes hit, you get this. A sudden catastrophic voltage drop, which we call an IR drop. Just look at that insane dip. In a tiny fraction of a nanosecond, the voltage just plummets. That is our silent killer. It's a super brief but totally devastating power shortage that can corrupt your data or just crash your whole system. So how in the world do you fight something that happens that fast? Well, that leads us right into section 2, capturing the switching storm. You need a tool that can see these lightning-fast events as they're happening. And that tool, my friends, is dynamic IR analysis. So what is it really? At its heart, dynamic IR analysis is this incredibly powerful simulation. It's not looking at averages anymore. No, it models the chip's behavior at the exact moment a transistor flips from a 0 to a 1 or a 1 to a 0. It's all about capturing the real instantaneous burst of current drawn during those split-second changes. Now, to do this right, the simulation has to get incredibly detailed, almost character-driven. It treats the little parts of the chip, the cells that are actively switching, as the main characters, the active current sources, demanding power right now. Meanwhile, all the other cells that are just sitting idle, they're basically just part of the scenery, passive loads. This separation is totally key to understanding who's causing the power demand and when. Okay, so let's see how all this detailed modeling comes together in a full-blown simulation. In section 3, we're going to look at how engineers simulate a chip's real behavior, all before a single piece of silicon is ever made. You've basically got two main flavors of this simulation. First up is vectorless analysis. This is where the computer tool itself just goes wild, generating millions of hypothetical what-if scenarios to try and find weak spots. It's awesome for getting broad coverage early in the design process. And then you have vectored analysis. This is where engineers feed the simulation real-world stuff, like the data from running a video game or a video call, to get razor-sharp accuracy on how the chip will actually behave. But here's the thing. You don't actually have to choose just one. In the real world, engineers are smart about it. They use a hybrid approach. They'll use the broad vectorless analysis to check everything, and then they'll unleash the super intense vectored analysis to stress test the most critical parts of the chip with hyper-realistic situations. It's really about getting the best of both worlds, high coverage and pinpoint accuracy where it matters most. The whole thing is a really methodical process. It goes something like this. First, the tool maps out the chip's power grid, like an electrical blueprint. Then, it figures out the power demands and generates all those switching scenarios we just talked about. After that, it runs the big simulation over time to see what happens. And finally, it spits out a report, pinpointing exactly where and when those dangerous voltage drops are happening. And that report, that's where the magic really happens. This brings us to our final section, finding and fixing hotspots. This is where all that analysis finally turns into real, concrete action. Oh man, this slide just says it all, doesn't it? On the left, you've got a map of switching activity. The red areas are where tons of transistors are firing at the same time. Now look at the right. That's the IR drop map. See it? The hotspots line up perfectly. It's so clear. Where the chip is working the hardest, the voltage is dropping the lowest. This is the smoking gun engineers are looking for. So what's actually causing these hotspots? Well, it usually boils down to a few usual suspects. Maybe the power grid itself is just too weak, like trying to drink a milkshake through a tiny coffee stir. Or maybe you've got too many power-hungry cells all crammed together, all screaming for energy at the same time. Sometimes it's just one cell trying to do too much work, and the local voltage just can't keep up. So the simulation flashes a big red warning sign on one of these hotspots. Now what? What's in the engineer's toolbox to actually fix the problem? Well, they've got a bunch of options. The most straightforward fix is just to beef up the power grid itself, basically add more lanes to the electrical highway. They can also just physically move the busy cells apart so they're not all drawing power from the same spot. Sometimes they can even tweak a cell to make it use less power. But one of the absolute coolest solutions is to add something called a decap cell. A decap cell it's brilliant. It's basically a tiny local battery placed right next to a power-hungry area. Think of it like having a small water tower right next to a factory. When that factory suddenly needs a huge burst of water, the local tower can supply it instantly so the water pressure for the whole city doesn't drop. These on-chip batteries do the exact same thing, but for electricity. It's such a clever fix. So, as we wrap this up, it's pretty clear that dynamic IR analysis is so much more than just a simulation. It's a critical diagnostic tool. It lets designers see into the future to predict and prevent these invisible electrical storms, making sure the chips that run our entire world are tough and reliable. And that leaves us with one final, huge question. As we keep packing more and more power into smaller and smaller spaces, how are we going to evolve our tools to predict and prevent these insanely complex electrical storms? Not just when they happen, but before they can even begin to form. The future of all our technology pretty much depends on finding the answer.